Okay, to finish up gas laws, we're going to look at this problem using a little bit of Dalton's law of partial pressures and all of our formula that go with that. And then we'll finish it up with the kinetic molecular theory of gases. Okay, so for this problem, we have a sample here that has some impurities. So there's a 0.2 gram sample, and it's, like I said, not completely pure. The sample contains sodium azide, so NaN3 is sodium, and then this anion here, N3 minus, is called azide. Okay, so one of the properties of sodium azide is that when it's heated, it decomposes into sodium metal and nitrogen gas. So in older airbags, this is the reaction that would happen inside your airbag, and this happens very, very quickly to produce lots and lots of nitrogen. Okay, so we're going to heat this up. We're going to decompose. We're going to produce the nitrogen gas. We are going to collect it over water. So this was filled to the top with water. As the nitrogen gas is produced, it kicks the water out, and it then is the nitrogen gas is then collected here where the volume can be measured. Okay, so this reaction was done at a temperature of 31 degrees Celsius. The atmospheric pressure, so the atmospheric pressure outside, and then because these water levels are equal, the pressure inside here is equal to the pressure outside here. At this temperature, the pressure of water, the vapor pressure of water, is 33.7 torr, and this was done at a wet volume of the gas mixture, so the nitrogen in the water. So volume wet is 63.5 milliliters. Okay, so the first thing we want to know, what is the dry volume of N2? So for example, what this means is if we were able to conduct this experiment and say collect the gas into some sort of evacuated or some sort of tube under vacuum where we could straight up just measure the volume of N2 produced, what would that be? And then number two, we want to know what is the mass of sodium azide that was in the sample. Okay, so let's start with number one. So we want to know the volume of dry N2. So we're going to use some relationships between gas mixtures. So here's kind of a list of formula we talked about for using with gas mixtures. So we have Dalton's law, where the pressure, the total pressure in a gas, is equal to the adding up the partial pressures of the components. The total pressure inside a mixture is equal to the total moles RT over V. The pressure of just gas A is equal to moles of A RT over V. Pressure of A is equal to moles of A over the total moles times the total pressure. And then we have pressure of A over pressure total equals moles of A over moles total equals volume A over volume total. Okay, so if we go back and look what's given to us, we have the total pressure because the atmospheric pressure equals the pressure inside. And since we are given the vapor pressure of water, we can find our pressure of N2. So we'll be able to use this formula here to get our pressure of N2. So say our pressure of A, then we'll have PT and PA. So then we can use PA over PT equals VA over VT. Okay, so let's go ahead and start with that. So we want to look at some pressure. So we have our total pressure. So pressure total equals 1 atmosphere, which we also know is 760 torr. Okay, so we know that that total pressure is equal to pressure of N2 plus pressure of H2O. Okay, so 760 torr is equal to pressure of N2 plus our pressure of H2O at this temperature is 33.7. So 33.7 torr. which leaves our pressure of N2. Okay, so write that down. Our pressure of N2, when we solve that, is 726.3 torr. Okay, so we don't necessarily have to, but if we want to turn this back into atmospheres, that's 0.9557 atmospheres. Okay, so just converting that back to atmospheres. We didn't necessarily need to do that, but I will need that later in the problem. Okay, so now our volume of N2 over volume total equals pressure of N2 over pressure total. Okay, so I'm going to rearrange this so that I have volume of N2 equals pressure N2 over pressure total times volume total. Okay, so let's go ahead and solve. Vn2 is equal to, okay, let's put in our pressure. I'm using atmospheres, but it doesn't matter. You can use torr. 0.9557 over 1 times our total volume. If you look back up here, that was the 63.5. So if we were conducting this, again, into some sort of system where we did not have to have water in there, we would have expected to collect, I got 60.7 milliliters of gas. So that would have been the dry volume. Again, if we didn't have that water mixed in there. Okay, so just using some of our mixture formulas there, not so bad to solve for that. Okay, so the next part, we want to know the mass of sodium azide in the sample. So to have the mass of sodium azide, we're going to have to do some mole calculations here. Okay, so we're going to look back at what we have and get that set up. So let's take a look at some of our formula we have for mixture. So we are still dealing with a mixture here. We still have the water in there. We still measured all that. So we want a way to solve for the moles of nitrogen gas we produce. So if we take a look, we have this one here, which looks promising, but we don't know the moles of water. So we can't figure out our moles total. We don't have anything to indicate that. We just have the ratio. So that's not going to be super helpful. So if we look at something else we have, again, this is just another version of this. That's not going to help us. If we look up here, this probably looks like what we're going to have to use. We do have pressure of A. We solved for that. We have moles of A, or we are after moles of A. We know R. T was given in the problem, and we do know the volume. So this is the total volume. Okay, so in the conference last time, I made the mistake of putting volume of A down here. This is not volume of A. This is our volume of mixture. So that total volume gives us that particular pressure. So it is important. Again, going back to our original formula, we use the total volume. Okay, so this looks like our guy. So if we do some rearranging of this, we can get the following. Okay, so if I solve for moles of A, okay, so if I solve for moles of A, we get Na equals, so again, multiplying that over volume times pressure of A, and then we would divide over the RT divided by RT. So we're going to have volume, the pressure of just gas A, over R times T. Okay, so let's plug some values in and solve. So number of moles of N2, okay? So it's going to be our pressure of just N2. So that's our right here. So we have 0.9557 atmospheres times our total volume. So that was the 63.5. I'm going to turn that into liters. So we get 0.0635 5 liters. Okay, good. Divided by R, 0.08206 liter atmospheres per mole Kelvin, and then times our temperature in Kelvin. So that was 31 degrees Celsius. So that's 304 Kelvin. Okay, so if we solve for moles, all of our units cancel, atmospheres cancel, liters cancels, Kelvin cancels, and we're just left with moles. So when we solve, I got 0.00245 moles of N2. Okay, so in that container, in that gas mixture, we had 0.002435 moles of just N2. Okay, so now to work backwards to figure out how much sodium azide we initially had in there, just a little bit of stoichiometry. So 0.002435 moles of N2. Okay, going back to the reaction up here, we have a 3:2 ratio. So we have 2 mole of NaN3 divided by 3 mole of N2. And then we're going to multiply that by the molar mass, which is 65 grams of NaN3 per 1 mole. Okay, so let's punch this in and solve it. Okay, so we have our 0.00245 multiplied by 2 divided by 3 and then multiplied by that 65. So equals 0.106 grams of NaN3. Okay, so that's how many grams of the sodium azide we had, according to our calculations here. Okay, so if we look that initial sample with the 0.2 grams with all those impurities, only about half of it was sodium azide. And again, the whole sort of point of this problem was kind of like a lot of them that we've looked at, find a way that your target will react. So in this case, we use the fact that with heat, it decomposes to form nitrogen gas. We could collect that nitrogen gas and then work backwards to see how much of the original compound we had in our sample. So it turns out, again, it was, a little over half of it was the sodium azide. Okay, so but kind of looking back for this problem, again, why I wanted to do another one of these is that I did sort of go back to all of my formula that involve mixtures. So that's important. When you have a mixture of gases, you're going to pull from what you need from this list of formula here. These all have to do with mixtures of gases. Okay, so you can get where you need to go by using one of these formula. Okay, so now back to sort of the other things we need to cover in this chapter, and that is the kinetic molecular theory. Okay, so the kinetic molecular theory has to deal with the motion of gas particles to explain the behavior of gases. So we kind of do know a few things about gases before even looking at this. Number one, we know that gases expand to fill a container, that they are homogeneous, that we can compress them, we can expand them, that they're zooming around with this sort of fast motion, all of that stuff. So all of that kind of comes from this kinetic molecular theory. Okay, so number one, there are a large number of particles moving around in rapid random motion. So there's no current in a gas, is essentially saying. All the gases are moving in random places. You don't have gas particles moving together in one direction. It's all completely random. Number two, we've kind of talked about this. There's a large space between particles, and that allows us to compress gases where we're just reducing that empty space between particles. There are no attractive or repulsive forces between particles, and we did talk about that when we talked about the ideal gas law. Some gases do slightly attract or repel, but for the most part, because of that large empty space between particles, you don't really get much attraction or repulsion between gas particles. Number four, the average kinetic energy does not change when particles collide. So this is important. This means that when particles collide with each other and with, say, the walls of the container, they don't lose energy. And again, that's important because if that wasn't true, then eventually gas particles would collide so much that they would lose all energy, and then all gases, pretty much without any external stimuli, would reach 0 Kelvin eventually. And we know that that's not true because you can store a gas in a container almost indefinitely without much change in the temperature. Okay, and number five, the average kinetic energy is proportional to the absolute temperature. So heat up a sample, you increase the speed or the kinetic energy of the particles. Vice versa, if you lower the temperature, the gas particles are moving much slower. Okay, so with all this, putting all of this together, you can derive the ideal gas law from this, but also we use it to look at the distribution of speeds. So this is a Maxwell distribution. So a Maxwell distribution is not your sort of classical symmetric bell-shaped curve. If this was bell-shaped, all three of these would occur at the peak of this, but that's not how this works. So it's kind of steeper on this side and then tails off on this side. So what that means is over here on this side of the distribution, you have less values than you do over here. And again, you have that tail. Okay, so when we solve a Maxwell sort of distribution for gases, we get this, equation up here. Not at all important. What is important are these 2 points here. So this one has a third. Your book only talks about VP, which is the most probable, and VRMS, which is the root mean square speed, which is the average kinetic energy. We also have this one, which is the mean. So the mean would be the difference between the minimum value here and the maximum value over here. Will give you your mean. But again, not super important. We are going to look at most probable, so that highest point on the peak, and the root mean square speed, which represents the kinetic energy of the sample. Okay, so we just need these two formula right here, which are also given in your book, but we will sort of box them here. So the first one is this. So this one that I'm boxing here in blue, that is our most probable speed. So this is the formula that we can use to get our most probable. So our root mean square speed, we use this one here. So the only difference between them is the constant. Okay, so to solve or to calculate this, it's 2 RT over M, where M represents the molar mass of the gas. And for this one, it's 3 RT over M, where M is the molar mass. Again, and sorry, with the square root. Okay, so that's how those are calculated. So we can calculate the points up here by just 2 RT over M, square root, and this point here, which again represents the kinetic energy, square root of 3 RT over M. So you see for the speed of a gas, so the most probable speed, or the speed that represents the kinetic energy of the sample, all we need to know is the temperature of the gas and the molar mass of the gas. Okay, so both of these only depend on temperature and molar mass. 2 and R or 3 and R are both constants. So just temperature and molar mass. Okay, so we want to do this here. So we want to, calculate the root mean square speed of a sample of hydrogen at 50 degrees Celsius. So again, only things we need are the molar mass, which we can get because we know the identity, and the temperature. So this asks for root mean square speed. So your book uses U, it doesn't really matter. So speed root mean square is equal to the square root of 3 RT over M. Okay, so 3 RT over M. Okay, so let's just start plugging away here. Grab my notes. Okay, so 3 we've got. So a couple of things. For this one here, we have to put things in proper units. Okay, so this is a speed. So speed is in some sort of distance unit per time unit. So if we think about our SI units, when all this is said and done, we're calculating the speed of this gas in meters per second. So that means we're going to have very interesting units here. Okay, so let's think about the units for R. We had 2 units for R. We had liter atmosphere per mole Kelvin, and we have joules per mole Kelvin. So it turns out for this problem, we're going to use R as equaling 8.314 joules per mole Kelvin. And we're going to use this version of R because we can take joule, which is also a derived unit. 1 joule is equal to a kilogram meter squared per second squared. Okay, so if we're taking a square root of something like this, so we can get the kilograms to cancel if we have meter squared per second squared. If we take the square root, we're going to get a speed in meters per second. So you can probably guess what's going to happen. M is going to be again, it's molar mass. So molar mass, so think about molar mass, we usually report that in grams per mole. But to get our kilograms to cancel, we're going to change the molar mass. Instead of grams per mole, we're going to use kilograms per mole. Okay, so now if we look, mole is going to end up canceling with mole there. Kelvin here will cancel with Kelvin here. So we'll get mole and Kelvin gone. So that's gone to kilogram will cancel with kilogram. So under the square root, we're just going to be left with meters squared per second squared. After we take the square root, bingo, meters per second. Okay, so interesting units, like I said. So root means square speed is going to be square root here of 3 times R. So 8.314. Okay, so I'm going to substitute this in for the joule. So kilograms meters squared per mole Kelvin second squared. Okay, now we need the temperature. So it's 50 degrees Celsius, which is 323 Kelvin, divided by the molar mass. So this is H2, which is a little over 2 grams per mole. So it's 2.02 grams per mole times 1 kilogram per 1,000 grams. So I'm just going to slap that together here. So grams cancels with grams. But if you say wanted to convert this first before putting in here, that's totally fine. Okay, so let's take a look. Make sure all of these crazy units cancel. Okay, so I already did this one. Grams cancels with grams. Per mole cancels with per mole. Kilogram cancels with kilogram. Kelvin cancels with Kelvin. We're left with meters squared per second squared, which is great because once we take the square root, that will turn into just plain meters per second. Okay, so calculate So punch this in your calculator. Make sure you come up with the same thing I did. 2 times 10 to the third meters per second. So the average kinetic energy of the gas particle, so the speed that those particles are going to have the average kinetic energy of the sample, is about 2.00 times 10 to the third, or 2,000 meters per second. So that's how fast those gas particles are traveling. Okay, so gas particles do travel really, really fast. So when we saw that here, at just regular 50 degrees Celsius, hydrogen gas, on average, are traveling around 2,000 meters per second. Okay, so want to go back to something else. I want to go back to this sheet. So if you're following along with the notes, we are going to flip this over to the other side. Okay, so I want to look at comparing a couple of things here. Okay, so we saw from the other side, and when we did our calculations, so again, when we looked at our formula, depends on molar mass and temperature. So I want to look at changing temperature and changing molar mass and how that affects the curve. Okay, so the first one we're going to look at is mass of gases. So we have all 4 of these gases at the same temperature. Okay, so we have O2, N2, H2O, and helium. These are all at the same temperature. Okay, so what does it look like is happening here? Let's take a look at sort of some molar masses. So for oxygen, for O2, here we can write some, or write on here. So again, it depends on the mass of the gas. So O2 is around 32 grams per mole, N2 28 grams per mole, water 18 grams per mole, and helium 4 grams per mole, with some decimal places there. Okay, so what does it look like is happening? Which gas appears to have a faster, we'll say, most probable speed? Okay, if you look, helium, the top of the peak, because that's the easiest sort of thing to compare. So the top of the peak for helium is over 1,000 meters per second. For the other gases, far sort of below that. Oxygen, the lowest value, then nitrogen, then water, and then again helium much farther out. So if you look, the top of these two are so close together because their masses are pretty close. And then oxygen a little further out. And then this one, because it's so much lighter than the other ones, has a huge drastic difference. Okay, so not only do I notice that, but if you look at the shape of the curve, helium has a much, much larger tail. That means helium has far more speeds that it has available to the particles as well. So this one goes from about 0 to 1,000 for oxygen. So its speeds are sort of in the range of 0 to 1,000 for that particular mass. For nitrogen, it tails off a little bit further, so a little bit more than 1,000, like, I don't know, 1,000 and like 1,100, say. For water, even further out, now we're like halfway between, maybe like 1,300, from 0 to 1,300. For helium, this range of speeds from 0 to almost 2,500 meters per second. So not only on average are the average speeds are a lot less, but when you have a much lighter gas, you have a much larger distribution of speed. Okay, and we see that by looking at the range. Okay, so the question, what is the relationship between speed and particle mass? And we saw here that the larger the particle mass, or the larger the molecular atom mass, the slower the speed. So big, heavy gases are slower, which probably isn't entirely shocking, because we did see that speed and temperature, they are proportional to one another. Okay, so here, and since temperature was in the numerator, not entirely shocking there. Oh, excuse me, I did the wrong one. Mass is down here. I was like, wait, that's not right. So speed and mass of the particles are inversely proportional. So our oxygen with the larger mass resulted in slower speeds. Sorry. Okay, so now let's look at temperature. So the second plot. Okay, so second plot here looking at temperature. So this is now the same gas. It's N2 at 1, 2, 3, 4 different temperatures. So we have 300 Kelvin, 600 Kelvin, 900 Kelvin, and 1200 Kelvin. Okay, so what seems to be happening here? As the temperature goes up, the average speed or the root mean square speed or whatever you want to talk about is also going up. Okay, so the shape of the plot is changing very similar to what we saw above, where not only is, say, that average speed getting larger, or most probable, speed getting faster, but also the range is extending with temperature as well. So the range going from here to here, more. Again, as the temperature increases, we are extending out that range as well. Okay, so same kind of similar trend, but now we're looking at temperature. So these ones are directly proportional. As temperature increases, speed increases. And we see this here. Temperature, see I got it right this time, and speed are directly proportional because this is in the numerator. Okay, so and again, talking about this one, when we increased, we got that sort of flatter curve with the larger distribution of speeds, just like we saw with helium up there with our nice lighter gas. Okay, so this is sort of the kinetic molecular theory, and this is how, again, the distribution of speeds is affected with mass and also with temperature. So mass inversely, temperature directly proportional. All right, so to finish off this is like the topic that never ends. We're going to look at what are called rates of effusion and diffusion. So you've probably heard of diffusion before. Diffusion spreading in space, like if we were to spray some perfume in one part of a room and eventually we would be able to smell it everywhere. That is diffusion. So it's just spreading in space. Effusion with the E is escaping through a pinhole. So looking at gases, the rate at which a gas can escape through a pinhole. Okay, so we're just diffusion, that's nice. We're not going to do any calculations with this. We are going to do a couple of calculations with effusion. So the effusion rate, which we're going to call R, is proportional to the speed of gas. So the root mean square speed, the average speed, the mean speed, doesn't matter. Pick one, they're proportional. So if we were going to compare two gases, we have gas 1 that has speed or rate of diffusion 1, molar mass 1, and gas 2, rate of effusion 2, molar mass 2. So I chose the root mean square speed here to compare. So for gas 1, that rate would be proportional to 3RT over its molar mass, square root. For 2, 3RT over molar mass 2, square root. So if I want to compare two gases, I want to compare, say, how much faster or slower is R1 compared to R2, I can take the ratio of the two. So R1 divided by R2 would equal, so now I can turn this into an equal because whatever constant we would have here to make these equal would just divide out here. So R1 over R2 equals square root of 3RT over molar mass 1 divided by 3RT over molar mass 2. So if we get all of our constants to cancel, so 3 cancels with 3, R cancels, T cancels, so all of those cancel. What we're left with is R1 over R2 equals the square root of molar mass 2 over molar mass 1. So you're probably thinking like, no, you wrote that wrong with all your mistakes you've been making here recently. But I actually did okay on this time because this would turn into 1 over molar mass 1. It should be 1 over molar mass 2, which if you just sort of put them where they're supposed to go without having all those fractions, this would go into the numerator and this would go into the denominator to give a square root of molar mass 2 over molar mass 1. Okay, so for our effusion for your formula sheet, rate 1 over rate 2, where 1 and 2 are different gases, is equal to the square root molar mass 2 over molar mass 1. Put a box around that. That is how we can compare the rates of effusion of two gases. So we're not going to, calculate absolute rates like, 500 meters per second. We're going to be able to say something like gas 1 would effuse twice as fast as gas 1. So that's really what we're going to be able to say here. We're going to say how much faster a gas would rate, 1.5 times or, 0.5 times, whatever we happen to solve for that. Okay, so we have a practice problem, so we can kind of see how this works. So for this one, we have two gases in a balloon. So we have C3H8 and we have O2 in a balloon with a pinhole. So that's my pinhole right there. Which gas will effuse faster and how many times faster? Okay, so let's look at our molar masses. So molar mass of C3H8. Okay, we'll do that one first. So that is 3 times 12 plus 8 times 1. So I got 44 grams per mole. And if we go molar mass of O2, we get 2 times 16, which gives us 32 grams per mole. Okay, so we know rate is directly proportional to temperature. So these two gases, since they're in the same container, have to be at the same temperature. So that's not a factor here. So the faster gas is going to be the one with the lower or smaller mass. So remember, it was inversely proportional to mass. So which gas will effuse faster? So the answer to that is O2. And we know that is true because it has the lower molar mass. And how many times faster? So now we can use our formula to compare the rates. Okay, so I want my answer to be in terms of O2 since I know it's faster. So I'm going to put O2 in the numerator. RO2 over RC3H8. And again, I know this one's faster, so I want to put it in the numerator to get so if this is larger or faster than this, then this ratio is greater than 1. And I don't know about you, but fractions maybe not something that's super fun to deal with. Okay, so that is the square root of, okay, so molar mass 2, which is this one, is going to go up here. And that is my 44 divided by, and my O2 will be down here. That's my 32 gram per mole. Okay, so if I solve this, I get 1.173. So 44 divided by 32, the answer to that, take the square root, I get 1.173. So what does this mean? RO2 is 1.173 times faster than C3H8. Okay, so it will come through faster, 1.173 times faster than C3H8. So it doesn't seem like a whole lot, and I mean, O2 is coming through faster, not significantly, and that's because their masses are pretty close together. If we would have chose something, a lot larger, like maybe like xenon hexafluoride, we would have seen a huge difference here because xenon hexafluoride is going to have a really, really large molar mass. So that's a big, heavy gas. So we would see a really large difference in the rates of effusion. Okay, so this is finally it for chapter 10. So again, kind of a recap with what we did with the kinetic molecular theory, knowing your two sort of formulas for calculating the root mean square speed. And we're, okay, so our two formula here. So again, have these on your formula sheets. The most probable, so at the top of the peak, and the root mean square, which is the kinetic energy speed. So having these two on your formula sheet and practicing using those, setting them up with the weird units that they have. And then also this one here, when we're comparing two gases, to be able to put them in the appropriate places and solve for that.